Okay, hey guys. Welcome to Biophysics class 27. And this class is on micelles versus planar bilayers. And you'll remember that a few days ago, before our interruptions in our education, we were talking about micelles, and this is really a tale of one-tailed and two-tailed amphiphiles. Um, Remember that a one-tailed amphiphile, like the one at left here, which is called SDS, which has a hydrophobic and hydrophilic tail, can form into a spherical micelle here with an optimal number n of amphiphiles in it. And so therefore, with an optimal number n of amphiphiles, it would have an optimal size. And this is certainly done and micelles play functions, as we said, in the digestive system to encapsulate vitamins for easy absorption in the digestive system. So these do play a role, certainly these micelles biologically. And we had a theory, which I won't get into now, of you can check your notes for when the concentration of these one-tailed amphiphiles increased. Uh, Initially, the one-tailed amphiophile concentration increased up to a critical value at which the amphiphiles started to form their with their structures with optimal N, and then after that, the micelles, the N amphiphile micelles started to dominate, and the monomers, the amphiphile monomers, leveled off. So, however, for a two-tailed amphiphile, like the one below, which is called PC, for the phosphate and choline groups, which are in it. See, it has two hydrophobic tails. These two tails here are hydrophobic. Turns out it's not possible to find this arrangement in a micelle, as there's simply not room for all these double tails to fit inside with the hydrophilic heads on the surface geometrically. And you will actually argue this in our class exercise when we meet. You'll put together a geometric argument. So instead, two-tailed amphiphiles form bilayer membranes, like the cell membrane, as we've seen. So in doing so, we have the hydrophilic heads on the outside and the hydrophobic tails, two of them, on the inside. And with this structure, there's enough, geometrically enough room to fit these double hydrophilic tails inside and to hide them from the water. So properties of bilayers and the advantage of curvature. So bilayers, like the cell membrane, entail more energy savings than micelles for a two-tailed amphiphile, since they can hide the two tails from the aqueous cytoplasm. Also, bilayer membranes that are a few nanometers across, which is a typical size, give useful and desirable values for properties of the membrane, like mechanical stiffness and permeability to ions like chlorine or sodium or potassium, with the exception of dedicated ion channels in nerve and heart cells. And we'll look at the nerve cells, the neurons, near the end of the semester. So, however, there's an issue here, and that is the edges of the planar bilayers, if they're in a linear arrangement here, expose some hydrophobic tails. So these tails here, if this at some endpoint of this linear bilayer, these tails would be exposed, and that's an energy penalty. So it turns out that overall, it's advantageous for these bilayers to gently curve into a closed structure. The curvature actually imposes a small free energy penalty, but it's more than offset by hiding these exposed hydrophobic tails. And this forms what's called a bilayer vesicle, which can be seen as here. In contrast to the micelle, where all of the tails reach into the center, here we have two layers, one inside the other, with heads and double tails facing one another. Okay, so we see that it's curved into a bilayer structure called a bilayer vesicle. But from looking at this, we can't really tell if it's a cross section of a sphere, which it could be, if there's a two-dimensional object, a sphere, which it could be, like the great circle of a sphere, or a cross-section of a cylinder, which extends in and outwards from the into the screen. And so next time we'll actually compare cylinders and spheres using a free energy model to determine which one is more common in the cell. Okay, so to summarize, we've seen that micelles are useful for certain biological mechanisms, such as absorption of vitamins. They involve single tails, single hydrophobic tails. However, for double hydrophobic tails, we need bilayer membranes, which have nice properties. But the bilayer membranes tend to, for free energy reasons, to hide the exposed hydrophobic tails, tend to curve into a closed structure, which we call a bilayer vesicle. So we'll investigate more this. We'll investigate more how this fitting of double tails in our in-class exercise today. In our next in-class exercise, and then next class we'll explore cylinders and spheres. Okay, that's it. Thanks for your attention, and see you in the next class.